Hi, my name is Anshul, and I'm a PhD student at the EDAP Research Institute and EPFL.
Hi, my name is Samy, and I'm also a PhD student at the EDAP Research Institute and EPFL. And the following presentation is an introduction to our work on multimodal gaze targets prediction, which was done in collaboration with Dr. Jean-Marc Odobez.
Our work is titled A Modular Multimodal Architecture for Gaze Target Prediction, Application to Privacy-Sensitive Settings. To begin, the task of gaze target prediction involves predicting whether a person is looking inside or outside the frame, and to regress the 2D gaze target location. Here we have a small video demo of our model running on a sample clip. The task involves understanding of both the person and the scene. Typically, humans leverage several cues for this task, such as the context and person activity, the gaze direction of the person, salient items in the field of view, and priors about the 3D scene structure. Typical approaches use a two-branch architecture, where the human branch processes the head crop of the person to implicitly or explicitly model their field of view. And the scene branch processes the full scene to learn salient items for gaze. Finally, there's a fusion of outputs from both the branches. The issue with this approach is that the cues we spoke about earlier, such as context, salient items, and 3D scene structure, must be implicitly learned from gaze data. While this could be possible, the issue is that this would require a large amount of diverse data and large models. So the question we would like to answer is, can providing explicit cues improve gaze target prediction? And can we learn from less data? In the form of explicit cues, we try to leverage pose and depth information. Pose provides the location of body parts, such as the hands and faces, which are common gaze targets during interaction and manipulation activities. And depth provides the object shapes and gives an idea about the 3D scene structure. So we know whether a person's looked at the front or the back, and it helps resolve ambiguities along the line of sight. A second motivation is to use our model for privacy-sensitive applications. In such applications, such as healthcare and surveillance, the identifying information, such as faces, cannot be revealed. And so training data cannot be shared. However, if we have processed data, such as depth maps and pose maps, which do not contain identifying information, then the data could be shared and we could train some models. So a question we would like to answer is, can we perform gaze target prediction using only depth and pose information? In summary, we have three major contributions in this paper. We propose a modular multimodal architecture with attention, which combines information from multiple modalities. We investigate applications to the privacy-sensitive setting, and we also study some technical elements. Moving on to our method, our architecture has three major components: a human-centric module, a scene-centric module, and a prediction module. The human-centric module takes as input the cropped head of the person and outputs a gaze cone. This models the field of view of the person. The scene-centric module, specifically the feature extractor submodule, takes as input the different modalities and the outputs of the human-centric module, which are the head mask and the gaze cone, to output a set of modality-specific feature maps. The attention submodule then performs a linear combination of these feature maps to give a combined feature map. The weights for the combination are predicted for each sample. The prediction module then takes the combined feature map and a gaze embedding from the human-centric module to regress the gaze target heat map and the in versus out gaze label. In the privacy case, we do not process the image modality, and the human-centric module takes as input the head skeleton of the person instead of the head crop. We perform experiments on two public benchmarks. The GazeFollow dataset is an image dataset, whereas the video attention target dataset is a video dataset. A point to note is that video attention target has high resolution frames and more gaze targets on faces. We perform experiments using single modalities and multiple modalities. We also perform experiments in the privacy setting and perform some ablations to test the technical elements. For quantitative results on GazeFollow, the image model performs the best among single modality models. This makes sense as the image contains all the information. This is followed by the depth model and then the pose model. This can be reasoned with the fact that the pose modality has some information, which is the gaze targets on objects. The multimodal model has improved performance compared to the single modality model. In fact, it achieves state-of-the-art results on all metrics. The average attention scores also reflect the importance of the different modalities, with the image having the highest weight, followed by depth, then pose. In the privacy setting, the multimodal model has improved performance compared to the single modality models. And in fact, it has comparable results to the image-only model, which is quite interesting. On video attention target, The image model again gives the best performance among single modality models. In fact, the difference here is that the depth and pose models now have comparable performance, which can be reasoned with the fact that video attention target has more gaze points on faces. The multimodal model again has improved performance compared to the single modality models and has comparable performance to the state of the art. The average attention scores also reflect the importance of the individual modalities, with image having the highest weight and depth and pose having comparable weights. In the privacy setting, the multimodal model again has improved performance compared to the single modality models and has comparable results to several baseline models. We also perform some ablations and note that skip connections during the upsampling improve performance, and early fusion of person information is better than late fusion. Here we have some qualitative results. In the first case, the gaze target is on an object, and so the image has the highest weight. In the second case, the gaze target is on a face, so the image and pose modalities have the highest weights. And finally, in the third case, the gaze target is on the baby, which is not represented in the pose map, and so the image and depth maps have the highest weight. Interestingly, in the third case, although the single modality models perform poorly, the multimodal model is still able to effectively combine information and give accurate results. Finally, in summary, we have proposed a modular multimodal architecture with attention. This explicitly leverages the pose and depth modalities. The attention gives sample-specific weights to the modalities, and the architecture can be naturally extended for other modalities. We also showed that this architecture can be applied for privacy-sensitive applications. Some limitations, however, include the fact that our architecture does not use temporal information, and we currently use scene-level attention weights and may want to consider some other attention mechanisms. Thank you for your attention.